All right, and we're live. Cool. So welcome everybody to the Utah Go User Meet for the month of May. Just a reminder that the microphones in this room are very good. So if you're having side conversations, people online will definitely be participating in that. So just be conscious. So they're the squares above you with the green lights. Jobs and hiring. So we have some new people here today. If you're interested in looking for jobs, if you have jobs to post and are looking for engineers, the Forge Slack is the best place to find that. And we're gonna, I'm sure, hang out afterwards. So if you have questions about how to get on there, how to get involved, that's the best place to have conversations around jobs and hiring, as well as just about Go in general. Anybody who wants to speak, we say this every time, we are super open to the community and want to have lots of different people talk about lots of different topics. There's this paper call link in case you want to submit a paper or a talk proposal for us to go over, but it doesn't have to be that formal. If you just have an idea that you want to run past us, even if it's not a full talk, please, talk to us about it. We'd love to get you up here and hear what you have to say about Go. So I'm going to go ahead and turn the time over to Ryan Berger now. How Go optimizes your code. I'm sorry, I can't read.
Yeah. No problem. Yeah. Cool. Let's see. Alrighty. Oh, do I just share my screen here?
Yep. So you'll present and then
we need to stop presenting, present again to get it come back full size on the screen. If I had a mouse for that little tablet, I could probably full size it, but
I think you just do this.
you got it.
Yeah, beautiful. Okay. Good. Show. Cool. Okay, cool. Hello all. This is my second time talking about the Go compiler at this meetup. The first time I was here, it was generics. I'm not a type system expert though, at all. I tried my best, but I am an optimizations kind of guru. I did research in college on compiler optimizations and compiler correctness. This is kind of my wheelhouse. I'm here to talk to you today about how the Go compiler, Go, optimizes your code. I do work at Starbucks. I am an application engineer, internal tooling stuff. This has nothing to do with my job. I just thought I'd let y'all know that I work somewhere. So why or when to care about the compiler optimization? So most of you have probably dealt with memory issues because the garbage collector is being a little slow, or you're allocating a little too much memory, or maybe something is taking a little bit more CPU time than you expected. So you put that into pprof, you kind of gather up all the data that you can, and you make some strides in optimizing it from 100 milliseconds down to 10 milliseconds, and that works for you. That makes your customers happy. Your API is really fast. That's very awesome. At some level, though, you might hit a wall because there's something underneath you that's kind of a little less stable, because we're actually really, really bad at writing compilers that can optimize code. It's really hard to write compilers that can optimize correct code. And so you might find that the Go compiler is going to be your enemy here. Essentially, yeah, no matter how much you profile, no matter what you do, your code gen is going, at the end of the day, is going to be what decides how fast you are at some levels, especially in mathematical. So I have an example from Josh here. Josh, I believe he previously worked at PaleScale. He and I have been talking a bunch. You may see him again later in the presentation. Another comment from him. But he opened this issue with MD5 on Go, where he notes that the hand-optimized assembly for MD5 that runs on most Go applications is not performing as well as Go is not performing as well as the hand-optimized assembly version. Why is that the case? And one of the things that he points out is that the Go compiler takes A plus B plus C plus D and turns it into A plus B plus C plus D. Instead, it should use this. And that's a very subtle difference, but it's a really important difference because you can see here, if you're thinking as a processor, you have to wait for C plus D to finish before you can the B plus that result and the A plus all of that result. And processors nowadays are smart enough that they can understand that the next couple of instructions aren't dependent on each other, and it can run them not quite in parallel. It's not exactly how it works, but they can run them kind of next to each other, and you get a pretty decent speed up on that. This is something that's still not in the Go compiler. I posted something on the Forge Slack. It should be in the Go compiler soon. I have a patch for this, but this is something that you really can't get out pprof or like kind of messing around with stuff. I mean, I guess you could go through and try to like balance them yourself. After I wrote the compiler optimization, I wouldn't want to go try to balance that myself. That would just be hell. It would be awful to try to do that and force the compiler to compile the code that I have there. So I wouldn't recommend it. So now hopefully you understand a little bit what's important, why you might want to start caring about compiler optimizations. I'm going to try to give you an undergraduate compilers course in about like 30 minutes, and so that you can start understanding compiler optimizations, how you can start implementing them in the Go compiler, because it's actually not as hard as it sounds. There's just some concepts that you got to know first before you can get into the deep end. So compilers used to not be called compilers. It used to be called automatic programming. Grace Hopper talked about this, about automatic programming, where you have some language that you punch into a punch card, you feed it through the machine, and you get a new punch card, and then you feed that into another machine, and that's your program that gets run. Around the same time, there's this lovely John Backus quote: "The experience with slow automatic programming systems, plus their own experience with the problems of organizing loops and address modification, and convince programmers that efficient programming was something that could not be automated." And my guess is that it's probably kind of still true today, because most of you have probably fought with a compiler before. It's not very fun to fight with a compiler, but most of the time they work, and most of the time they do a really good job. But when they don't, they really suck. So it's kind of, you know, you have this lovely technology, but it's pretty hard to fight with it. And then we have our first, it's hard to say the first on all these things, but the first optimizing compiler being Fortran. They started noticing that they could start rewriting mathematical expressions that physicists were using. And they said, hey, maybe the compiler could rewrite this to make it a little bit easier on registers so that we can do programs faster. And then the big innovation that we're going to be kind of touching on today is SSA, or static single assignment. It comes along in the 70s at IBM, and it's a compiler analysis technique that allows people to reason about code a lot easier, because if you don't have SSA, you end up having to reason about graphs versus kind of a more linear list of instructions, and graphs are a little harder to reason about than just a linear list of something. It also is, you know, right after this, C gets, well, right around then, C is also written. Ken Thompson, the guy who wrote the original Go compiler in C, he wrote C as well, but he definitely kind of comes from this era in compiler technology, and it definitely kind of shows in some of the older Go compiler stuff. They ported some stuff, they were working on kind of modernizing some stuff, but there's definitely kind of some weirdness in the Go compiler. And that's kind of why I leave the here, because after here, there's tons of stuff, analysis, tools, but Go, like, I'm not trying to say that Go is old tech at all. It's not, but it definitely kind of has a very old vibe to it. I don't know if any of you have ever seen this before or ever heard about stages of a compiler, but generally we try to break up pieces of the compiler so that we're not doing it all at once. Sorry, I forgot to mention, feel free to stop me at any time and ask me questions, because I understand this is dense. If there's anything that isn't clear, then feel free to interrupt me. We try to break this up because it's a lot easier to reason in chunks than it is to reason about a text file turning into assembly. That's really, really hard to do. So first we lex it out. We turn a bunch of text into a bunch of tokens. We parse it. We analyze those tokens. We say, are these valid? And we group them together. We turn them into AST, some abstract syntax tree. You may have heard of these. It's used a lot in like interpreters, and you'll see them around in math expressions. But essentially, you turn something that is like a token plus token, a token, to a node that's of type binary operation, which is a plus would be a binary operation. And then you have two leafs, which are your A and your A. And you turn it into that. You type check it all up. And you make sure that all the types kind of make sense. And then this is kind of where most compiler courses or most compiler tutorials kind of stop, because this is the easy part, right? Once you start getting into more complex analysis and optimizing compilers, then you're probably going to want something called an intermediate representation. And all modern compilers use some sort of intermediate representation. So there's a Go that you guys don't see. There's a Go that the Go developers, the Go compiler developers know, and they use it to optimize your code, and they can reason about it. And it's a lot easier to reason about than it is to reason about your Go code. And then they apply a bunch of layers of optimization and shoot it out to an object file, which then the object file can get linked, and then you have an executable at the end. So that's kind of a normal-ish compiler. This is the Go compiler. So you can see that there's like a lot of things that are the same. And then we have the noter, which is like a really weird stage in here somewhere that mostly comes from the old Go compiler when it was written in C. This still exists. This was, I think Russ Cox wrote a C to Go transpiler to take the old C compiler or old Go C compiler and turn it into Go. So after the noter, you have the middle end is what they call it. The middle end it has legacy optimizations. It has some really basic optimizations because there are some really easy optimizations it could do there. And this is where inlining, what happened?
You slept.
My computer shouldn't sleep. Here, let me. Oh, did I get kicked out? What?
Damn.
Oh, I lost my network connection.
Oh, there you go.
Wow.
Weave rocks, right?
Yeah.
Not anymore.
Let's see.
Yeah, it's new.
Okay, can I get added back? Sorry about that.
Yep.
Okay.
Yep, go ahead and click in.
Window.
A little bit of excitement.
Yeah, serious.
We're on our
Yeah,
edge of our
on our
seats.
toes, yeah,
And-
you're on our seats, yeah, on the edge of your seats with this. Okay, cool.
Yeah, there
Yeah,
we go.
so this is where inlining and escape analysis happens. These are two kind of sore spots with the compiler. You might fight with the inliner, you might fight with escape analysis a lot. This happens here. There's some efforts to push it down below, but right now it's not. That's also where PGO happens because inlining also happens there. So a lot of the PGO stuff gets injected at this stage. Yeah,
Ego is.
you don't know what PGO
I
is.
don't know what ego is.
So it's profile guided optimization. It was released in 1.19 or 1.20. The idea is that you can run a program over and over again. And you can let the inliner view your profiles and say that method is called a lot in a hot loop. We don't want to make a method call. Instead, we want to copy your method and put it into your loop, and it's in a hot loop, and it speeds up your program quite a bit. So PGO is Go's team. Honestly, it's pretty PGO profile guided optimization is a pretty modern technique to squeeze a little bit more out of your compilers, because compilers just kind of have heuristics. They kind of make a guess about what most programs would do. They don't really know how many times you call that loop or call a function inside that loop. They kind of make a guess and they say, well, it will actually impact your binary size by inlining something. It will blow it up. We're not going to do that. We'd rather not, even though it could be a huge performance gain.
So the Go part here is coincidence. It's not a Go specific concept. It just happens to have Go in there.
Yeah, it happens to
Okay.
be called P. Yes,
It's a
exactly.
compiler concept.
PGO, yeah,
Okay.
yeah, exactly. So after your middle end, you have walk, which is like a desugar or a canonicalization pass, which is a fancy word for saying the compiler developers really don't like when you pass a struct with two fields in. They prefer to a function. They prefer two parameters on that function. They prefer to not think about the struct as a struct. They want to think about it as a couple of fields in the function. And I would prefer it that way as well in most cases. And then as soon as they're done with that, making it all nice and good and pretty, then they do this fancy thing called SSA, static single assignment, which we'll talk about in a second. And they run their internal optimization passes, which we'll talk about also. That's kind of my bulk of my talk is down here. This stuff is kind of boring. You're probably not going to, I mean, you probably will contribute in there sometime, but it's a lot easier to contribute in this area and get actual real performance benefits. And it's not too terribly hard to do either. Okay, so a single static assignment form makes for an easier analysis of code. Sorry, I'm gonna have to read this. So every variable must be assigned exactly once before it's used. That sounds right? Like I have to assign a variable before it's used. So each definition must dominate its use is another fancy way of saying that. So any definition that's defined, no matter how branchy your code is, in all code paths have to be defined before you get to a point. That is different than if you think like you can have if statements where there's like variables inside of there. You could have like crazy control flow. It's different than probably what your normal programming language does. But it takes something like this where x is equal to 10, x is equal to x plus 1. If I were to write an optimization for this, I'm walking essentially a graph where I'm saying, okay, well, you know, there's this plus operation and I need to assign it to x, and it gets all messy where I have to check for cycles because I'm referencing x from x, and I have this x that's assigned here too. I'm doing like, there's crazy cycle stuff. I don't want to think about that. Instead, I linearize it. So I kind of version each thing of x, because if you ever use x after this, you're not using this x, you're using this x actually, right? Is that kind of intuitive, right? You're not, this value goes away after this happens. So we don't need it anymore really. So we just version them. So this is x and this is x sub 1. Some, functional programming languages force this upon you essentially, because they say it's unmutable. You can only use this like, variable one, or you can only assign this variable once, goes not that way. So compiler developers want to linearize your code so that it makes our lives a lot easier. All good? Yeah. Okay. Okay. So some SSA-based optimizations, and it looked, I missed a piece here. Oops. So 3 really easy optimizations for us here that we're going to take a look at. We have our dead code optimizer. This one's really easy. This was supposed to be like x is equal to 1, and I guess I forgot. But we can start talking about how many uses something has, because we have a version of a variable for everything, right? We don't ever use the same thing over and over. We can ask how many times is it used, and if it's used 0 times, that means that we can get rid of it essentially. So y is equal to x plus x. In this case, y is never used. Its uses are 0. And it's pretty easy to remove y. There's nothing wrong with removing y. We're pretty happy because the number of uses, we kind of typically keep track of that, is 0. We don't have to worry about it. We can say that x is equal to 1 and return x. That's not too typical, not really hard. Next, we have constant propagation. If you have a constant somewhere in your code, it turns out that lots of times, instead of storing it in a register, because this is essentially what it may end up doing, it may be better to put your constant in and substitute it out for your variable name everywhere it's used, because 1, it's better for other optimizations, and 2, it might save a register, because a lot of CPU platforms let you use immediates or constants in the instruction names. So we take y equals x plus x and turn it to y is equal to 1 plus 1, and then we return y. And then the last one is constant folding. So I took this one here and I just put it up here because constant propagation and constant folding go together really well. Constant folding is when you take an operation with all constant operands, 1 plus 1, it's all constant. There's no problem with the compiler doing 1 plus 1 ahead of time for you so that you're not doing an extra add instruction. Yes.
Then drop the x as well.
So now we're going to get to that in just a second. Yeah. So, okay. You're getting there. Y equals 2 and return y. Okay, so these are optimization passes that run on your Go code. These are just like, hopefully it was pretty dead simple to see how easy it is to just count uses or move constants around. And that's kind of what SSA enables you to do. It's a lot easier to think about. It's a lot easier to reason about. And when you're messing with Go compiler optimizations, this is how you're going to be doing it. You don't have to reason about a lot of the harder things. So now, Carson had a great question. He was saying, well, on the last slide, we had, here, I'll show it again. On the last slide, we had this, you can notice that x becomes no longer used because we have a y equals 2 and return y. And as x is equal to 1, the problem here is that there's this idea called path ordering. So you have dead code that maybe runs, constant propagation that runs, and then constant folding that runs. But now we have a bunch of dead code in here. And so now we need to run dead code on it. And maybe that will cause some more constant propagation that we could do. And then that could also, there's some foldable things. And then maybe there's some more dead code because of that. And now the question is, like, is it better to, well, it's normally better to do constant propagation than folding. But the question is, like, how do you order those passes? And that's called pass ordering. And it's really, 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 really hard. It's like NP hard. It's like impossible to solve. It's something that compiler developers deal with to this day, and you gotta be really careful about. So Josh said, phase ordering is compiler's DNS to web services, except you can fix DNS, which is, I mean, it's questionable whether or not you can fix DNS, but you can't fix phase ordering or pass ordering problems. It's just really, really, really hard to reason about how to run these things and not end up running your compiler forever. Go and most compilers take a pretty reasonable approach, and they say, we're going to run for some fixed number of iterations. If we stop changing, if we run these 5 passes 1,000 times, and we stop changing any time in between there, then that means that our optimizations can do no more work. If we pass that, then we'll stop, because we're just going to keep running forever, and who knows how long it will run. And there's actually compiler warnings. I applaud you if you have ever seen them in your code. The compiler will start spouting warnings to you like, hey, your code just like caused us to run a lot of optimization passes. Like, please report this to compiler developers because there's something kind of up. I don't know if anybody's seen it, but congrats, you kind of win the compiler game if you have. Let's see. Yeah, so SSA optimizations in Go. So path ordering is hard. I don't want any of you to have to think about it. It's really it's kind of masochistic to go through a compiler and have to figure out where you want to put your path, how often you want to run it, sort of deal. But Go kind of makes this easy, actually. They have what are called rewrite rules. This is pretty common in compilers nowadays. They write a little cute language that says, whenever I see an add add operation, turn it into a, whatever operation. And so they have written this nice little DSL that you can use in order to pattern match on specific instructions. And then you can transform them into specific instructions. So this one is actually constant folding. This is an 8-bit number, 2 8-bit constants, and C plus D. It turns it into just a single constant, C plus D. And it does that. And well, actually, it's just a go generate command. So the Go compiler will go through and parse this sucker, and then it notices that this is a Go expression, and it will put it in a Go file. So like the Go generate will like actually build out some of these expressions. And some of the expressions are that you see if you ever go looking through its this directory right here in the Go source command, compile internal SSA. It's really long, but any whole file that you look through, you can see some pretty gnarly expressions in here. Like, it's just Go. There's nothing fancy. They also have helper methods too for your compiler optimizations. One thing that this is the documentation. It actually misses out on. I just copy paste the documentation, but you can actually put conditions in here too. So you could say like a really good compiler optimization is anytime you are multiplying by a power of 2. So multiply by 2, 4, 8, 16, 32. Multiplies are expensive, shifts are not. So left shift by log of whatever you're shifting by. So if you can guarantee that what you're shifting by is a power of 2, then you should turn it into a shift. Or if you're dividing by something by a power of 2, you should turn that into a right shift. And those are implemented in this language. There's no extra fancy compiler magic that you have to look at. It just looks like this. And they have some is power, is log 2, and that you can pass in stuff. So there's conditionals so that you can be a little bit more correct rather than just saying like turn all divisions into shifts, because that would really suck. So this is also how Go, an aside, but this is how Go turns like its like internal form, like adding a char up into assembly. It's just a bunch of these rules. And these rules are specific to architecture specific rules. So you'll see like when you're working around, you see like arm add W or whatever. And it's like, oh, like that's the arm one. Somebody wrote an arm rule specifically for adding arm instruction, like the add arm instruction. And that's just kind of how it is. It's actually kind of weird. There's some architectures, mostly ARM 64. Whoever optimized ARM 64 did a really good job, but didn't put those rules in the generic rules. So like ARM actually has like some speed advantages here or there. We got some compiler optimizations to fire on ARM, but none of the other ones that were very generic. But anyway, so there's tons of different rules files, but the generics.rule file is kind of what you're looking for. And this is kind of the syntax, and this is kind of what you're looking at. And you just run go generate in there, and it just generates the pattern matching, and it generates the output. Yes.
So all of these optimizations, specifically the SSA rules,
Yeah.
are run every time you do go build,
Yep.
and it's still lightning fast.
It's blazing fast. Yeah. There's probably a couple, probably 10,000 rules-ish or more. It's pretty quick. Yeah. Yeah. Don't add a bunch of rules in here. Yeah, they're going to be very mad at you if you do that. But yeah, it's really fast to do this. So yes.
Does go generate follow the build cache? Like if you don't change a file, does it still?
Like don't change a rule file or what?
So like if you don't touch a file and you run a build, it'll use a cached.
Yes.
File, right?
Yeah. So if you have like a package that it built, I think it's per package. So if if you don't touch a package, then it has a build cache that it pulls from for that package. And it's already run these. It actually stores it in like an SSA-like format as a cache. And then when it's time to compile everything together, it pulls all the SSA back, and then it does its thing, and then it spits out a binary.
So worst case, they still try to cache it.
They do, right? Yeah, they do try to cache it. And I mean, again, Go is still compiled so fast compared to most compiler platforms. That's kind of one thing that, yeah. Oh, sorry, I thought I heard somebody, but yeah, Go is really, really fast compared to most compiler platforms, just because like the LLVM folks don't care how long it takes. They prefer it to be just blazing fast and insane optimizations typically. Not the compile time. They want their programs to be fast at the cost of anything, right? So they're willing to let Google servers sit for 1,000 CPU hours CPU years to compile a silly little thing, so that it could just be lightning quick. Go, not so much. So I thought that we'd write a quick little SSA optimization, because I found one that's not in the Go compiler. I thought I might as well show it off here. We can write it and talk a little bit about compiler correctness. Okay, so this is how it typically works. You read some math code that looks really bad, and you're like, hey, that doesn't look right. The Go compiler should be smarter than that. The Go compiler is doing some math that I don't think it should be doing. It should be doing it ahead of time for me. And so you think up an observation. For example, key or not key is always true. If it's not checking, like the Go compiler is not checking for that, I didn't look. You definitely should go add that in there. Go compiler developers would be really happy. P or not P is always true. It's just how it is. It's tautology. We should do that ahead of time. What if some dumb junior developer put P or not P in some tight loop that you didn't know about, and then it gets optimized away, and then you have less branches? That's awesome. So here's my observation that I found. X is less than X plus 1. That's always true. And addition is 1 cycle, comparison is 1 cycle, and any sort of branch instructions, since this is a Boolean expression that you're using this with, you're jumping somewhere, which is a ton of cycles. So we save a bunch of cycles by doing this optimization, and it sounds worth it to me. So it's not too hard. So this is this is kind of how I have the before and after, what it would look like after running a bunch of optimization passes. But essentially, we choose our operation, which is less. We're working with 64-bit integers, and then we name some variable. We say it's C, which is our X on this side. We say there's going to be some variable C. I don't really care where it comes from, what sort of operation it is. It doesn't matter. But on the right-hand side, kind of this sub-expression here, we know that if it's going to be our C or our X plus 1, and we're going to turn that into a constant Boolean of true. And then we run go generate, and we compile our code, and this is true, which means that the Go compiler will run as dead code and all that fun stuff, and you'll get this panic right here. It will just turn into this. If you had any extra work down here, yes.
I should probably ask first, does Go have integer overflows?
I knew you were going to say that. Wait for it. Wait for it. Okay. Wait for it. Okay. There, that was the dramatic reveal. Okay.
I'm so sorry.
So, anyway.
I'm so sorry.
Yeah, the X is less than X. It's like, damn it, Todd. I was hoping that I moved over fast enough. Okay, oh well. Anyway, so you can turn, right? You can essentially put these little variables in here. It's A, B, C, and D. That's their variable names. You can do A, B, C, and D. There's I think you can add a couple, but they're reserved. Don't use A, B, C, and D unless you're using it for this. Like if there's like other sorts of variables that you can use. But yeah, anyway, A, B, C, and D is kind of what you're looking at. So sorry, I didn't choose C. It's what the Go compilers chose when they wrote their little DSL. So yeah, A, B, C, and D. So we chose our C here, and yeah, okay. So okay, so compiler optimization work is really hard, right? It's really tricky and really, really subtle. I spent the last couple weeks working on that compiler optimization that Josh talked about. And when you miscompile an addition somewhere, just who knows where, in some just odd function, and it just messes. Well, and then you use the compiled compiler that you just built, you just optimize with your new fancy optimization, then run things, then addition stops working in some certain cases. And it's like, now you've blown your Go tool chain up because addition doesn't work. And it's like, oh boy, like you gotta go hunt down where that little tiny addition is. It's really, really tricky to hunt stuff down. And so the LLVM people are a little bit more, what's the word? Rigorous about this. They really want to make sure that their optimizations are, oh my goodness, why I keep getting disconnected. What happened here? Yeah, network disconnected.
Yeah. Power saving.
Yeah, I guess.
It honestly might be.
Oh,
If your computer,
Why would the compiler router be power saving?
It's not going, I don't think it's going to sleep.
yeah, that was my suggestion.
I said, I'm pretty sure I turned it off.
Change that network.
Okay.
So maybe it's like.
Here, I'll present. There we
It
go.
adds to the tension every time, don't worry
Yeah,
about
I know. Okay.
We'll cut this out.
Okay, thank you.
it. And Todd, just blame Todd. It's-
Yeah, we're gonna blame Todd for this, for all of this. So the LLVM folks are a lot more rigorous about this, because their code is running on missile systems. And they would prefer their missile systems to hit the right people, although maybe they don't, I don't know. That's kind of up to them to decide. Or for example, I guess I don't, I mean, it's being recorded. I think it's fine. So I did research in college, trying to make sure that compilers compile ARM code correctly, because Toyota uses ARM, and there have been certain incidents about Toyota cars that were software defects that they don't really particularly have a root cause for, and so they want to say that it might be a compiler bug. And they worry that using old compiler tool chains might have old compiler bugs in them. So we prefer a much safer to use compiler with compiler optimizations that are correct, because compiler optimizations are hard to write. So I built this tool that was based off some of my research in college called Golang TV. It just takes the ARM verification stuff and it extends it to let me work on Go. So I wanted to really quickly do a live demo, if that's just fine. So essentially here, I'm sharing, I'm not sharing my whole screen. I am really good at this. Okay, stop presenting a window or your entire screen. Okay, let's see. Entire screen. Wow. Okay. Hey, let's see. Maybe. Here we go. Okay, cool. So, here we are in my little Going TV project. It's a little bit hard coded and stuff, but this is kind of how it works typically. I mean, it should be hard coded this way. So I have a source function and I have a target function. And the idea is that I want to take some source function and I want to, the fancy compiler word for, you know, a transformation between one operation to another is a refinement. You can lose information between refinements. So it's a, use your words carefully when talking with the Go developers and compiler developers in general. But we want to refine the source into the target. We want to say that a valid refinement of x is less than x plus 1 is true. And we'll ask a really fancy, it's called an SMT solver. It's, I don't know if you've heard of SAT, it's like SAT, Boolean satisfiability, but essentially we can actually give it x is less than x plus 1. It understands how integer math works and how integer comparison works. It understands Booleans and all that fun stuff. It understands memory. It can understand a lot of things. And you can ask it, is for some input, do the states of the program differ? That's what we're really worried about as compiler developers is whether or not the states differ. So let's run this sucker, and I'll show you really quickly. This is what SSA, Go SSA looks like. These are your operations. Right here, yeah. So you have like add, int, v6, v8. These are your version numbered variables. Then you have your less, and it's getting, we just wrote a pattern matched version where it should pattern match this all in. Anyway, but beside the point, if we scroll down, there's a bunch of LLVM crap to help you debug things, but we kind of have a little bit of a problem. Damn it, Todd. So there's value mismatch. And what does that mean? Well, it means that it found some input x that x less than x plus 1 is not true. And it's correct. Overflow is the problem here. Signed overflow in particular. So it spits out that, hey, I have a true value that always gets returned, but if you pass in the maximum signed integer, then you get a negative integer. It wraps around, and then you have a problem. Yes.
Is it, I mean, I'm familiar with like fuzzing. It's not trying all possible integers, is it?
No. So it's a lot smarter than that. So it understands math at a really deep level that I don't understand how it understands that math. So another really common problem that it also solves is, I don't know if you've ever seen like, you have like A or B or C and D or E or F, and it asks for which inputs are A, B, C, D, E, F true? Like when does that expression become true? And that's kind of a known NP hard computer sciencey problem. And they leverage similar techniques, but they understand that we're within 2 to the 64. So we know that we have a finite space of integers. We can't brute force that space. We have smarter math to kind of figure out comparisons and all that fun stuff. And so it's, I mean, it's running on my commodity hardware, but it's using Z3 as the theorem prover is what it's called to prove that, hey, for these inputs, there's something wrong. And I'm also on top of Alive, which is built on top of Z3, which is confusing. But Alive was built by my old professor, but it does, Alive essentially teaches Z3 how to use memory, which is like bonkers, because you can prove that memory operations and pointers and all that fun stuff, like pointer operations and memory and all that stuff, it's the same. And it's kind of wild what this sucker can spit out. I can like mess with panic bound stuff. Maybe after this, we can like mess around with what programs it can compile, but it will spit out, hey, I noticed you wrote to address whatever, an integer that's 64-bit, and you wrote to this other address that's whatever, and now the memory state is mismatched. And guess what? You're wrong. But if everything matches up by the end, then you're good. And it actually does function calls too, which is another really hard one. It just takes a really long time. You don't want to run things with function calls. Typically, you want really simple code like this. Function calls get really a huge mess. Huge mess. just because of the number of possible things that can go wrong during a function call and sorts of results that you can get back. And then the bigger problem is that LLVM is not Go. So x is less than x plus 1 is like pretty valid in what's it called, in LLVM land. That's a valid compiler optimization for it to make. It can assume that x is less than x plus 1. Specifically in the Go spec, it says compiler developers may not assume that x is less than x plus 1, which is where I got this little cute example from, just to scare you guys, tell you how easy it is and then scare you guys, and then show my product. I think that's kind of the way that this typically works. It's good marketing.
Is there a reason they intentionally didn't include that originally?
X is less than x plus 1? Yeah, it gets really messy because essentially what happens is if you can assume that x is less than x plus 1, here, let me go back to my previous code or my slides. I think it kind of becomes slightly clear. Where is it? Oops, Reddit. Reddit. Okay, let's see. Okay, so there's a problem here. If we can assume that x is less than x plus 1, this panics all the time. Notice, if this is the overflow, then this doesn't panic. And so the compiler can optimize this panic out, which is really bad. You want your program to crash when x is, this is not true. And overflow is a thing, but C has decided that it's not. It could actually, you're a dumbass for trying to like write some code that overflows. You should have checked that. We assume for our purposes that it's not, because look at how much code it saves. If this is always true, then anything below that can be optimized out. And think about that in like a 1,000,000-line program. Think about how many little tiny opportunities it's getting to optimize the smallest things out. It's the same with divide by 0, actually. If you have like x divided by y, it can assume that y is always not 0, unless it can prove otherwise. Sometimes it can prove otherwise and be like, hey, you know, like that's not right. But most of the time it can't. So yeah, there's a good reason why x is less than x plus 1 is explicitly disallowed in the standard. And I was going to show an x divided by y example, but Go's too smart about it. Because Go checks to see if y is 0 first and panics if it is. And you can't optimize that out because a panic is a side effect-y thing. Panics, this is a side effect. This crashes your program. You're done if this is true, right? You should never, ever, ever be able to optimize this out. I don't know what the programmer's on here writing this, because this is almost always going to be true except for in one spot. But like, yeah, you should never optimize out like panics or divide by zeros or whatever. You could always assume that the user's wrong. And that's why C has lots of bugs, lots of like really fun memory vulnerabilities, because they can assume that your pointer's never null, and then null pointer text can go away. Sometimes it's a thing in the Linux kernel. There's plenty of articles about null pointer text disappearing because you can assume it's not null in some certain cases. Because so if you access a pointer and then in the next couple of lines you use it again, it can assume that first access failed, or it succeeded or failed, right? And if it succeeded, then of course we can continue on. But sometimes with like super deep optimization passes, it just goes away. And so then you end up using null pointers places. And then you get like really weird bugs where it should have crashed on a null pointer lookup and it didn't. It just was silent and it causes memory problems. And it's really, really gross. So there's good reason that the Go developers did it. Whether or not you ask my professor if that's a good idea, he might tell you a different answer, but there's good ideas behind it at least, because you get out of a certain class of bug. Compiler developers just can't write that sort of bug. It's just not possible for me to do that, which is why I didn't show it. I can do this. This is easy to lead you on it. Todd isn't smart ass and thinking about integrals. So anyway, I think, yeah, that's my presentation. You can take a look. I mean, I don't have anything really on my website right now. I do have this Going TV thing. It's open source. Y'all can use it. Probably have to talk to me to get it to build, because there's a lot of stuff to get it to build. You have to get LLVM built, you have to get Alive built, and then you have to build this. And that's it's not too hard, but for people who haven't built a LLVM before, it's a little bit tricky. It's a lot of work. So cool. That's it. Any questions? Any extra things?
I have a question.
Yeah.
So if you go back to an earlier slide
Yeah.
on the reusing variables,
Yes.
x and then x sub 1.
Yeah.
How does that look in memory? Because
Good question.
yeah.
Yeah, so there's a pass called registry allocation. So the idea is that we want to keep as many of our what's it called? As many of our operations and constants in memory as possible. And so assuming this wasn't constant propagated, because it would be, right?
Yep.
Just don't think about that. What we would want to do is we want to put this into a register, and then we would want to reference that register here. So we'd have like an add instruction. And so in memory, that's how it is. Alternatively, it can notice that we're out of registers at this point. Sometimes your program is using a lot of math and intermediate results, and we're running out of CPU registers, and it's called spilling. It spills that out to the stack, and then this will become a stack load. So there's register allocation is another path, and register allocation again becomes really easy with this sort of thing, because you can say these are registers, essentially CPU registers, but there are way more like variables in your program than there are CPU registers. And then it becomes an optimization problem of who do I keep in my registers and who do I spill off to the stack? And that's kind of what it looks like in memory. Yeah. Yes.
I'm gonna have two questions that
Yeah.
I'm not gonna like flush out anyone else. But one, you said something about how Go doesn't like to pass structs when you call a function. It passes the field as argument. Is that what's actually happening?
Yeah, you want me to do it? I'll do it for you.
Yes.
I'll do it in here.
You think structs are just syntactic sugar for?
Sometimes, not all the time.
I knew that about maps and slices.
I'm surprised, like, I always thought it was literally passing passing a value, but I guess.
It is passing the value.
Passing a lot
Yeah.
of value.
So yeah, so we could say, let's say P dot A is less than 0, and we can do this again. Hopefully this doesn't miscompile. I'm really sorry if it does. I've tried to test this a lot. I'm pretty sure I tested it with this test case, but it's hard to write a Go compiler by yourself. That's essentially, oh yeah, look at that. So if you look, it shows the struct. Is it? Oh, I turn it back into structs because I thought that was dumb. Yeah, it was harder to work with. Yeah, but it can. Yeah, absolutely. So that's a valid optimization, is to take this struct right here and turn it into, you're just passing A and B in, because otherwise it's doing like math lookup in the compiler, but yeah. Anyway, transformation seems to be correct. Are you kidding me? It thinks something's funky. It thinks, I don't know what it's on. It's thinking something weird.
That's a cool project though, like
Yeah.
clearly difficult.
Yeah, this was a couple 3 a.m. mornings crying about SeaGo. SeaGo is awful. Don't use it. It's just so. No, I'm kidding. But SeaGo is rough. So getting things to link and writing a C wrapper around a C++ API to get this to work was hellish. So also shout out to the TinyGo people, because the TinyGo people made this project possible, because otherwise I couldn't translate my Go into LLVM so easy. They have a huge library of stuff that let me do all of this pretty easy. It was just like writing a compiler. I didn't have to deal with LLVM. That was just terrible. Having to write a Go wrapper for LLVM. So they do that, and I try to contribute back. But yeah, it's a fun project. Okay, anyone? Yes.
So correct me if I'm wrong though.
Yeah.
In the case of the struct example, just to play with this a bit,
Yeah.
because usually a struct is represented as just contiguous values of the stack,
Yes.
and when pass into a function,
Yeah.
could pass in a pointer to the stack.
Yes. Okay.
But you
Yeah.
would rather use registers.
Yeah,
right?
yes, you got something right. So as of Go 117, I think it's 117, there is a register-based calling convention is what they called it. And you got like a 15% speed up for free. And the reason is because they started taking stack things that were stored on the stack, because that's what they used to do, is they used to store things on the stack. That's also how you're taught as like a student, is like store things on the stack because it's too hard to implement an API. But Go has other reasons because of Go routines and stuff. But yeah, so they said, okay, well, storing it on the stack and jumping and then having to load it back from the stack, that's a store, a jump, and then a load. Or we could do register loads, which is really fast. Then we can jump, and then we can do register stores, jump, register loads, which is really fast. But there's only so much register space, and Go only goes so far. If you pass a pointer to a struct, hand her off. It's not gonna be nice to you about that. It doesn't know whether or not it's coming in from the stack or the heap. It doesn't know. So it's not gonna be sugar things for you. It will just, it will do a memory operation for you. It will load. So yeah. Yeah, but the register-based calling convention is nice for when it can be used, but there's only a certain subset of registers that can be used because of Go routine complications. And I don't even know the Go API. I'm pretty bad at it. It's a lot of work. So. Other questions? And the recording, talk after, yeah.
Yeah, I will close that up. Thank you.
Yeah.